So in this video, we're going to start by looking at the general rule for computing the probability of f given E. So we have the general rule for computing the probability of f given E. If E and f are events in a sample space, then the probability of f given E equals the probability of E intersect f divided by the probability of E. So this is a lot like the rule we saw in the previous video, except the rule in the previous video we had the number of ways that event E and F could occur together. So we were looking at the intersection, but we were looking at the number of ways, and we were looking at the number of ways event E could occur. So it was N of E intersect F and N of E in that previous rule. Well, it also works out that we can do this with probabilities. So let's take a look at an example. Example 3. According to Vital Statistics reports, the probability that a newborn baby is preterm is 0.127. Also, the probability that a newborn baby is preterm and weighs 8 pounds 13 ounces or more is 0.002. What is the probability that a randomly selected newborn baby will weigh 8 pounds 13 ounces or more, given that the baby is preterm? So what we're given is that the probability of being preterm is 0.127. And we're given that the probability of being preterm and weighing 8 pounds 13 ounces or more, that probability is 0.002. So we're given the intersection. The probability of being both preterm and weighing 8 pounds 13 ounces or more is 0.002, and we're given the probability of being preterm. So this is like the probability of E. This is the probability of E and F. And we're asked, what is the probability that a randomly selected newborn baby will weigh 8 pounds 13 ounces or more, given that they're preterm? So we're asked to find the probability of 8 pounds 13 ounces or more, given that they're preterm. So this is our F given E. Well, according to our rule that we just saw, that's going to equal the probability of E and F, so in this case preterm and 8 pounds 13 ounces or more, so that's 0.002, divided by the probability of being preterm, which is 0.127 in this case. That's our P of E. So I'll get this probability just by taking 0.002 divided by 0.127. So 0.002 divided by 0.127, that is approximately 0.016 if I round to 3 places. So this is 0.016. So if we know the baby is preterm, the probability that the baby will weigh 8 pounds 13 ounces or more is 0.016. So not very likely. Now the rule that we just saw here can be converted into this next rule that we'll use more frequently. So this is the rule for computing the probability of the intersection of events. So if E and F are two events, the probability of E and F is equal to the probability of E times the probability of F given E. So this is actually the same rule that we just saw right here. The difference is we've solved this formula for the probability of E and F. So if we were to multiply both sides of this by P of E, we get this result right here. The probability of E intersect F equals the probability of E times the probability of F given E. So how do we use this? Well, take a look at example 4. Suppose 2 cards are drawn from a standard 52 card deck without replacement. What is the probability that A, both cards are face cards, B, both cards are aces, C, the first card is a face card, and the second card is an ace. So what we're looking for in this particular case, we're drawing two cards. So we want to know what is the probability that the first card is a face card and the second card is a face card. So the first card being a face card, that's like E. The second card being a face card, that's like F. So this is going to equal the probability of the first card being a face card times the probability that the second card is a face card, given that the first card is a face card. So that is our rule. The probability of E intersect F is equal to the probability of E times the probability of F given E. That's our rule. So the probability that the first card is a face card. Now again, we have seen our deck of cards several times now. There are 12 face cards out of 52 cards. So the probability that the first card is a face card is going to be 12 out of 52. And we looked back in example 1, the probability that the second card is a face card, given that the first card is a face card. Well, if the first card's a face card, there's only 11 face cards left in the deck, and there's only 51 cards left in the deck. So the probability that the second card's a face card, given that the first card's a face card, is 11 out of 51. So if I take 12 out of 52 times 11 out of 51, that's going to be our probability. Well, I'm just going to do that on my calculator here. 12 out of 52 times 11 out of 51, that is about a 0.050 probability if we round to 3 places. So this is going to be approximately 0.050. So the probability will be 0.050 that both cards will be face cards. Question B is a lot like question A. We want to know what's the probability both cards are aces. So we're going to look for the probability that the first card is an ace and the second card is an ace. I am shortening my verbiage here on my notation. So the probability the first card's an ace and the second card's an ace. So this is E, this is F. So that's going to equal the probability that the first card is an ace times the probability that the second card is an ace, given that the first card is an ace. Well, the probability that the first card's an ace, well, there are 4 aces out of the 52 cards, so that's going to be 4 out of 52. And the probability that the second card's an ace, given that the first card's an ace. Well, if the first card's an ace, then that means there's only 3 aces left in the deck for the second card to be an ace, and there's only 51 cards left in the deck. So it would be 4 out of 52 times 3 out of 51. So if I take 4 out of 52 times 3 out of 51, that is 0.005 if I round to 3 places. So this probability is 0.005. Now notice the difference here. This is 0.050, this is 0.005. So quite a bit of difference between those two. Question C. We want to know what's the probability the first card, that should be card with the D, what's the probability the first card is a face card and the second card is an ace. So what's the probability the first card is a face card and the second card is an ace? So the probability that the first is a face card and the second is an ace. That's what we're looking for. So this is E, this is F. So that's going to equal the probability that the first is a face card times the probability that the second is an ace, given that the first is a face card. Well, the probability that the first card is a face card is 12 out of 52 because there are 12 face cards in the deck of 52. Times the probability the second card's an ace, given that the first card's a face card. Well, if the first card's a face card, that means there's still 4 aces left in the deck for the second card. So there would be 4 aces out of 51 cards left in the deck. So if I take 12 out of 52 times 4 out of 51, that is equal to approximately 0.018. So this is about 0.018. So if I draw 2 cards out of the deck, the probability that the first card's a face card and the second card's an ace is 0.018. Let's take a look at example 5, still on this video. Repeat example 4, but this time with replacement. That is, replace the first card into the deck before drawing the second card. So in question A, we want to know what is the probability that both cards will be face cards. But again, the difference is here we did it without replacement. In example 5, we want to do it with replacement. So we're going to draw a card, put the card back in the deck, and draw another card. So how does that change things? Well, I'm not going to write out my notation, but the probability that both cards are face cards for the first part here, well, that's going to be the probability that the first card is a face card times the probability that the second card is a face card, given that the first card's a face card. Well, the probability that the first card will be a face card will be 12 out of 52. Now, the probability that the second card will be a face card will also be 12 out of 52 if we are replacing the first card into the deck. So if we draw the card out and then put it back in, there's still going to be 12 face cards in the deck, and there'll be 52 cards back in the deck. So if we make a replacement of that card, we get the same probability times itself. So if I take 12 out of 52 times 12 out of 52, that is a 0.053 probability. So this is 0.053 if I replace the card back into the deck before drawing out. Now notice that's a little higher than what we got when we did not replace. For question B, same idea. What's the probability both cards are aces? So the probability that both are aces, well, that's going to be the probability that the first card's an ace, which is 4 out of 52, times the probability the second card is an ace. Well, if we replace the card, the probability that the second card will be an ace will be 4 out of 52 again. So if I take 4 out of 52 times 4 out of 52, that is 0.006 if I round to 3 places. So 0.006 instead of 0.005 when we did not replace. Question C. What is the probability the first card's a face card and the second card's an ace? So the probability that the first is a face card and the second is an ace. Well, the probability the first card will be a face card will be 12 out of 52. And if we replace that card, the probability the second card will be an ace will be 4 out of 52. So the difference here is that if I replace the card, there's 52 cards here instead of 51 if I replace it. So if I pull in my calculator, 12 out of 52 times 4 out of 52, that is a 0.018 probability. So 0.018. Now there is a distinction between these two, but we can't see it when we round to 3 decimal places. So there is a difference. The probabilities aren't actually equal, but rounding to 3 places, there's not a big distinction on those two. So let's conclude this video here, and we'll pick up with the next example on the next video.